I don't know what went wrong with me yesterday, but I do apologize to everyone for whatever took place. My brain somehow is completely. I hope that's not going to be happen again today, but in fact, I wasn't really expecting anyone to come today, so I'm flattered. Um, So I was very exercised about what I should say today, obviously. In fact, I did in my mind have uh, titles for the talks 2, 3, and 4 of my 4. And today's was meant to be about scaling, as I said in my first lecture. But in fact, I was extremely helped in my thinking by Ibu Ba's lecture this morning when he listed the things that physicists believe quantum field theory ought to provide for them. And he said, well, mathematicians think about these things, they like definitions. And I'm obviously at the extreme mathematical end of this area of knowledge. And so it seemed like quite a good idea for me to try and get clear in my own mind. And then it occurred to me, why wouldn't it would be perhaps quite a good idea to say it to you too, what I believe the point of view I'm espousing has to do in the way of providing answers to the questions that he raised, or the things that he said a field theory should provide. Well, in fact, he listed, I wrote down 5 things when I was listening to his lecture, so I'll write them down here to remind you. So the first one was unitarity. And then there was locality. And then there was causality. And then there was renormalization. That's one of 4, I think I must have left one out. And one was cluster decomposition. And as he rightly said, these are not actually unrelated topics, but you can focus on them one at a time. Well, that's roughly the order he gave them in. Not the order I'm going to speak about then. I'm going to begin by saying a word about this. This is something which I personally have nothing really to contribute to, except a remark. In my first talk, I explained that quantum field theory started off historically by thinking of itself as the process of quantizing a wave-like system. One had a scalar field or a vector field or a bundle with a connection, some kind of functional space defined over a manifold that was meant to be physical space-time. And the original idea was that one was trying to quantize that. And then people decided that the best way to focus on the theories was in terms of the, remember I said we define a generalized Riemannian metric on the space of these configurations, these kinds of fields, whatever they are. And the system, classically at least, should go along a geodesic in that generalized metric. It should minimize the integral of that thing along the path the system describes in time. Well, so the remark that I want to make is just simply that in quantum field theory as it was developed, the crucial step was understanding the process of renormalization. And I don't want to say anything about that, but that's a very arcane and mysterious thing for most mathematicians. So it's what make quantum, only some Lagrangians make good sense, the ones for which you can actually do this process of renormalization. And what I want to point out for the sake of mathematicians is that the condition on a Lagrangian which, which allows you to be able to do this renormalization is exactly the one which is the natural condition in calculus of variations. If you, for example, well, I kind of half mentioned in my amused state yesterday, the example of two-dimensional quantum field theories. And I kind of vaguely meant to say that one of the obvious sources of field theories in principle in any dimension is sigma model. So these are things where the system you study is maps from your space-time manifold into some auxiliary manifold. Let's call it, I better not call it Z, hello. Well, let me just call it N for the moment. But we have some fixed manifold, and the things we're studying is maps from this into space, from space-time into this. Our space-time is the thing that we want to make a theory functorial in. And we're assuming that this has some kind of Riemannian metric. Well, if this had a Riemannian metric, then something you can call the energy of this map, which is the integral of the norm squared of the first derivative of the map. And for instance, if this is a one-dimensional space-time, people are rather familiar with the energy of a path, the integral of half the velocity squared along the path. And in that case, with a one-dimensional space-time, this time, we know there's a very good theory, and that if you start with a random smooth curve going from a point to a point, or for example, a random closed curve inside a conjugacy class in the fundamental group of the target space N, we know that there's a very good Morse theory for such things. You can simply go down the gradient of the energy of the path, with the gradient tracked downwards, which leads you to a geodesic. So in that one-dimensional case, the theory works perfectly. Two-dimensional theories, it is on the edge of working. It essentially works, but one has, it doesn't quite work. There's the phenomenon of bubbling, which has been the focus of an enormous amount of mathematical attention in the last quarter century. On the other hand, if you were to go any higher dimension, then the Morse theory is totally wrong. If you started with a three-dimensional manifold and map it into some kind of target, it doesn't matter much what the dimension of the target is. That's essentially irrelevant. But if you, for instance, were to start here with something three-dimensional higher, and you were to try to go down the gradient flow of the energy is always defined the same way, then what happens is that the manifold M would just simply disintegrate. Instead of sort of getting nicer and approaching some nice smooth harmonic, one would call the map harmonic if one got to a critical point of the thing. What happens is exactly the reverse. The thing kind of explodes into shreds, and it's like sort of trying, well, it's like trying to, it is trying to move backwards along a heat flow. It can't go backwards beyond the initial time. So that for me is a tremendously comforting thing, that that a geometrical approach to quantum field theory almost certainly must be somehow essentially right, because it exactly the geometry works exactly when you can make a renormalized theory. Well, I don't have anything to actually contribute to that, but I think it's helpful at the point of view. Well, the next thing, so the next thing I'll mention is unitarity. That's very simple and concrete. I gave a kind of not very precise definition of what I think a one way to define a quantum field theory as a functor from a category of cobordisms of space-time of an appropriate dimension to the category of vector spaces, topological vector spaces, and continuous maps. Well, there's one thing that follows immediately, sort of trivially from those axioms. When you have a cobordism from something M0 to M1, then one thing you can do, and certainly in these lectures, I'm always assuming that all my manifolds are oriented. You don't absolutely need to do that, but it certainly makes things a little bit clearer, at least in the first instance for me. We think of this as a cobordism from that to that, but you can also equally well, of course, think of it as a cobordism from this, but with its orientation reversed, to this with its orientation reversed. So any cobordism can actually be looked at two ways. Now, we want ones with Riemannian metrics. And when we reverse the orientation, I'd like you also to, we're going to be talking about complex metrics. So we're going to complex conjugate the complex metric. In the case of a Riemannian metric, that will make no difference. But in the case of a Lorentzian metric, it will change the direction of time, which is kind of appropriate, obviously. So what follows at once from the axioms is that if you think of um bar, the operators associated to the cobordism that way. So this will go then this will go from then they are always sorry, I need to say that. Put the bar there. Then these are always adjoint in the algebraic sense. In the natural sense that when you have a manifold M0, you can take M0 with reversed orientation and make a cobordism like that. That's just a cylinder twisted round. And this will give you so this is meant to be a Riemannian manifold, so the complex conjugation is not doing anything to the metric there. This will make this be the dual. This is a pairing between these two things. We'll give us a map like that. And the axioms of the theory, you know, the famous axiom where you do a S-bend kind of series of cobordisms, you also get a map from the complex numbers into this symbol. This is a duality automatically in the theory, and so that's one fundamental property. Now, if we want to talk about unitarity, we want to make further condition, which is that there's another thing you can do with the cobordism. Given this cobordism, we can think of it as a cobordism the same way, but take the complex conjugate metric and also reverse the orientation of this thing. So it's still a cobordism going from this to this, but that way. You see, previously we didn't change the manifold in the middle. This time we are changing the orientation in the middle. We going this way, we kept the orientation of this the same, changed the orientation of the ends, but also changed the direction they were going. So we were not changing the overall orientation. I found it incredibly confusing. It took me months and months and months and months to get this straight. And one always gets into arguments with people about it. Anyway, we want to assume, if we're going to be talking about unitary theories, that the operator associated to M bar is simply the complex conjugate of the area of that. So that's this is what we want to assume if we're going to have a unitary theory. And also, we want to assume this property of reflection positivity, which was mentioned this morning. Which precisely will say that this is a Hermitian non-degenerate, that this is a positive pairing, because it will now go from the wrong. Putting this together with this, you will get a Hermitian pairing on the vector spaces in the condition that when you take your M naught, which is part of some cobordism, this metric has the property that there's a reflection around it which changes the direction of the transverse thing, but leaves M naught itself fixed. So in other words, on this, the two different kinds of, well, this has to be have a completely real metric, a real positive metric. So it's a genuine ordinary Riemannian manifold. You can forget the fact that it's got a complex metric. This property allows you to identify the two different sources of M naught. And in that case, you want the pairing to be positive. That's the condition of reflection positivity. So that's what I have to say about unitarity. Now this locality was explained in this morning's lectures, is, well, one way of looking at this, what we heard this morning, is in terms of what's called the operator product expansion, which was we're in some manifold M, and we are interested in making observations at various points. And remember, in my lecture, I said we can associate to any point X in our space-time a space of observables OX, the topological vector space of it, by considering little neighborhoods getting smaller and smaller, converging in little balls containing X at the center. And looking at the space, I called it, let's call a typical one of these D. Remember, I considered the space associated to the boundary of D. And if you want to be really kind of technical, you should take the inverse limit of these spaces as the D, so to speak, tends down to the point X. You see, these form an inverse system because you think of them as being cobordisms going outwards, so to speak, radiating outwards the influence of what's happening at X. But we have a sequence of these things. These balls form under inclusion, of course, and this gives us a definition of things at point. And I explained how if you have a number, well, locality was the fact that if you, sorry, I'm getting confused with this, it was the fact that when you have several of these points getting closer and closer together, if you look at them from a certain distance off, so you look at the effect they will have, say, on some surface which we keep fixed surrounding the points which are going to come together, then you can expand the effect of these things as perceived elements here when allowed to propagate outwards to the space E associated with the boundaries of regions, you can expand them in terms of operators which just come from one particular point, say this one there. In the thing we were told this morning, the operator product expansion. And well, all I want to say is that that's the way that's what physicists have been doing for years and years, which now people call operatic multiplications or little disks operands or things like that. But I just wanted to emphasize that this little disk operand language is exactly the same as the language of operator product expansions, which physicists use, except that physicists do it quantitatively rather than not in the sense of homotopy theory, where it usually occurs in mathematics. I'll be saying a bit more about that in my final lecture.
I have an interpretation of what you mentioned this morning, that in a conformal theory you expect this expansion to be analytic, but in a general theory just asymptotic.
Gosh, that's a bit, yeah, that's a bit too clever for me. But yes, that's certainly true. But that would take us a long way afield, I think. Yeah. Then there's this question of causality, and that does relate to the things which I sort of said. Let me just mention cluster decomposition. The idea of working with manifolds with complex metrics was to allow one to use very freely this concept of Wick rotation, to say that you might as well work with the Riemannian manifolds the most perfectly. And of course, if you have this kind of picture, and you imagine a cluster of points here and a cluster of points here, and you want to see what the total output is over, say, a closed manifold M, which contains the two clusters, then of course one way of looking at what you're doing in the cluster expansion is to think of this as a cobordism from nothing to something there, and then you do a cobordism just a little way further, and then you do a cobordism out to where everything's gone away at time plus infinity. But now we're doing this all with Riemannian manifolds. The cluster thing is we make this little cylindrical bit get very, very long. You let that go far out. But remember, with a Riemannian manifold here, the operator associated with a thing like this is just exponentiating a positive operator if we have a unitary theory. So it will, whatever thing we got on out of this cluster, whatever we saw coming from here is some element of the vector space, the state space associated to that spatial slice. It gets strongly pushed down to a single vector, the vacuum vector, because of the contracting nature of theory. So we'll see only some multiples, so to speak, of the vacuum vector there. And then we'll see what effect this cluster has on it. So the things will factorize with, so to speak, a vacuum state in the middle. That's all I had to say about these. Now, the remaining thing is causality, which is perhaps a little bit more interesting, and which should have been part of yesterday's lecture. So actually, so we want to say that, well, now we always have the same picture. We have some space-time M, and now it's meant to be Lorentzian. And we want to say that if we have 2 points which is space-like separated, that means that we can't find any smooth curve which is time-like, which in the Lorentzian metric, the square of its infinitesimal length elements is always positive. That if we have a thing which can't be joined by any time-like curve, so they're space-like separated, then if we take points here, observables here, and observables there, they don't affect each other. In other words, when we think of them as operators, the operators will commute. Well, in order to make sense of that, we have to, what I did explain was that if this was a cobordism from something to something, then each element of this, supposing that was a cobordism from M0 to M1, in accordance with this morning's lecture, I've rotated time through 90 degrees. Each one of these things, remember, I did say, would give us map like that. We would think of it as an operator like that. But of course, it doesn't make sense to say that operators like that commute, because they're from something to something else. And the kind of space-time on which you can formulate this property is one which is what they call globally hyperbolic, which means that it can be split up in time slices, so that there are time-like, it's a complete it's a product of something with a unit interval in which the lines this way are like. So in particular, that means that all the different time slices are diffeomorphic to each other. By the way, I'm always working in practice with compact spatial slices, and that isn't the best thing to, I mean, that isn't the ultimate thing to do, but it's certainly a very good beginning. What one really should be talking about is space-like slices which are compact with boundary, and think about possible boundary conditions and how one might couple them and so on. But that's a much longer discussion. What one definitely shouldn't do is just start with a non-compact time slice with no knowledge, no prescriptions about what happens at infinity. If you did that, you would be losing all the simplicity of the mathematical analysis that quantum field theory has, and sort of one will be back in situations more like hydrodynamics, which is vastly more difficult mathematically from the point of view of analysis. Anyway, well, so if we have something like this that's globally hyperbolic, then all of these spaces, before we start putting in any observables or operators, can be identified with each other by this kind of propagation. And as we kind of tried to explain in our paper, when you rotate to the Lorentzian situation, these become unitary identifications. Well, now supposing on some particular, so that enables us to identify all of these things once and for all, and also enables one to ask the question, when you change this metric from being Lorentzian to being Riemannian. And well, so we can do the following thing. Now, we had this thing which we've decided to slice up into time slices. Supposing we look at this end and this end, or indeed any other slice, one of the things that it's very useful to do is to consider the neighboring slices on each side of the one you're interested in, so that you're looking at a little very thin cobordism here. And then you can look at the part of the space associated to this slice, which comes in from small times slightly before. They will have, if we make this Riemannian, a dense image in the vector space associated to the slice we're actually interested in. So it's like the way the heat flow pushes L2 functions, however little time you go, onto smooth functions. So inside this vector space, for any slice, we will always have, you think of it as being like a Hilbert space, we'll always have some dense subspace that you can think of as, like, say, the smooth function. Similarly, we can look at things going outwardly, and you will see that they correspond, you can imagine that they will correspond to the dual of the smooth function, which is the distributions. And of course, this little tiny coordinate is really the thing which we used to get the duality between those two things. We bent it round. So we have this nice situation of weak space where our spaces have dense subspaces and have nice completions. Well, what we should do is looking at this little thing here, we could, supposing we had several points on the same time slice, so they would be certainly space-like separated. We can put a little disk around each of them, which fits inside a little time slice, and you'll see that what you have is we identify all of these things. So I'll just say M dot for the generic one of these. What we will always have, if we take any X on, well, they're all the same. So we can, if on any time level we have a lot of these things, we can make something this is actually the tensor product of the spaces associated with all of those things. It will go from the dense subspace to the completion space. So with something, it'll be something like an operator with a distributional kernel, something that would only really make sense as an operator after you've smoothed it a bit. We will be able to put in lots of operators on the time slice, on any particular time slice, and we didn't, although I've written them in order across the page, it's clear that in making that construction, one hasn't used any ordering of the points. So we actually extend this to things which lie on the same time slice, and we have an operator which didn't depend on any choice of ordering. But now we can go back and see that if we had any two points like this, we could always put them on the same time slice simply by, you see, remember we have this theory defined for any kinds of our complex metrics. So we can push things around very freely. So we can take whatever we had, you know, I began by in whatever time slices we had, we could identify all the spaces, the vector spaces associated to them. If we had this global hyperbolicity property, we can see that any two points can be put on the same time slice, and therefore you have an operator which simply didn't depend on the ordering, and that gives you all that you need in the way of commuting at space-like distance, space-like separation. Well, there are a lot of slightly tricky points involved there with topological vector space and all sorts of things. And I won't try to say any more about it now. Actually, there was just one more thing I'd like to say about this situation. Something which I found extremely puzzling when I first thought about the subject. One thing I've said which you really should find somewhat fishy was when in an M we take some point, and I said take a little disk around it and consider all these disks getting smaller. Well, that's a fine thing to do in a ordinary real Riemannian manifold, it's not a very brilliant thing to do in something that's Lorentzian. I mean, what exactly do you mean by these things? You kind of can just ignore the metric and say you're interested in small neighborhoods of the points and they get small. But I mean, I think you're right to find it puzzling. And what I eventually realized, which should take away one's puzzlement, is there's a slightly different way of thinking of the concept of a complex metric, which is, I think, very helpful in this direction. Which is, remember yesterday, I made a real hash of trying to define the class of complex valued quadratic form on a real vector space. This was meant to be a quadratic form. Now, there are many ways of saying what I said, but one thing you can obviously do is extend this to the complexification so that it's complex quadratic form. And if it's then non-degenerate, then all such are the same up to automorphisms of V. So there's only one of these things. So you might as well choose some coordinates and think that V is contained in some standard vector space, CD. And the metric that you're going to be interested in is just induced from some embedding of a real d-dimensional subspace of which this is the complexification. Well, in fact, when you do that, you can, given a V, one way of thinking of those numbers, the angles that we wanted to add up to less than pi, one way of thinking of what those things are is that they're, if you think of the argument of this thing, the angle of the value of this thing, the thetas that we found are actually the critical values of the argument regarded as a function on the real projective space underlying V. And that helps in a lot of ways understanding metric. But all I need to say for this purpose over here is that you can ask yourself, given a complex vector space with a standard quadratic form on it, there's only one, what kind of subspaces V are the ones we want? Well, we don't want to say that the restriction has to be real, of course. What we have is an open, a contractible open subset of real structures on here. So in the Grassmannian of d-dimensional real subspaces of this, there's a contractible open subspace formed by these allowable complex metrics. And furthermore, so for each choice of this, if we imagine X as the center of this, we will, so to speak, have an OX formed with respect to V. If we imagine in terms of an exponential map or something from around V into our manifold, we will have candidates on a Lorentzian manifold for these things, OX, associated to any V in the complexified tangent space, which is allowable in the sense that we want. Now, well, we'd like to define OX as this, but that doesn't seem very sensible because we have this open set of V and all these things would all be different. But the thing that one is saved by the fact that these are actually all canonically isomorphic as you move V around. This was a thing which for Maxim Kontevich was absolutely the central point. And when we were writing our supposedly joint account of the subject, we had completely different philosophical point of view. For Maxime, any Riemannian manifold is really the real points of a complex manifold. And so he was very interested in the fact that, again, one thing that you find almost automatically from the theory is that if you take a complex, imagine you have your cobordism, imagine it's sort of going up like this, and imagine this whole thing can be complexified. Well, if so in particular, this can be moved around inside a complex manifold. And what happens is that the structure is is constant with respect to moving this real thing inside its complexification. That's very surprising. It's yeah. Well, I don't want to go into the whole discussion because it's quite a long discussion, and we wrote it out as carefully as we could in our paper. But if you're prepared to believe that you're really inside something which can be complexified, and of course locally that's undoubtedly always true. Any little bit of Riemannian manifold can certainly be complexified, and we can certainly do this kind of thing. Then there's no problem at all. There's a problem with the fact that a general compact or otherwise real space-time certainly is not, can't necessarily be complexified. A Riemannian manifold isn't necessarily the real part of a complex holomorphic manifold. That didn't bother Maxime at all. I mean, he really does believe that the world is really complex, and we like to live in a real structure, but that's kind of just prejudice or something. Whereas I was very concerned with trying to avoid, well, of course, you can complexify a manifold if it's real analytic, but not in general if it's just smooth. On the other hand, any smooth manifold, by Nash's theorem and so on, can be approximated to arbitrary precision by something real analytic. So very difficult to think of any experimental difference between these things. Nevertheless, I don't like to think of us as living in the complexification of the world that I think we live in. And there was quite a big difference between the two authors philosophically. He absolutely wouldn't get interested in the difference between real analytic and C infinity. And so our best theorem definitely assumes the things are real analytic. Anyway, it isn't actually relevant to that point. Well, so now that we come to the subject of this lecture, it's slightly late.
Excuse me.
So that was meant to be about scaling.
Excuse me, sorry. Before you move on, I wanted to, I'm sorry if you already clarified this, but are you saying that causality amounts to the mere existence of this extension? Or does it have to do more than that?
If I can speak, I'm terribly deaf. Can you speak a little bit louder?
Are you saying that causality amounts to the mere existence of this extension? Or is it more than that?
How do you mean the mere existence?
Like, I guess what I'm confused about is I don't have a good intuition for why you don't expect an extension like this if the points were time-like separated.
Why you don't expect the space-time to be part of a complex manifold, so to speak?
No, I mean, so you're saying that you're passing from you have operators at several points, and you're passing to a tensor product.
Yeah.
And you're saying that I now have a map on this larger tensor product. And it feels like that should be quite general, but maybe my intuition is wrong.
Yeah.
Like why? But I'm asking if the existence of this map for the tensor product, is that equivalent to causality, or I don't understand the claim.
Oh, well, I was taking causality in the sense it was described this morning simply as the property that observables at space-like separated points commute. And of course, in this, one probably isn't very interested in the space-time as a whole for that question, because it's a question that really pertains to some region, because although your Hilbert space really reflects all sorts of global structure, probably that's not relevant in the kind of questions where you're discussing causality. But I mean, I just wanted to say that locally, you can always put space-like points on the same time slice, and you have this procedure for saying you never used any ordering anyway, you see.
I see, okay.
A bit, I mean, you think of the operators as passing in a little tiny slice, and then you say that all these slices can be identified by the cobordisms, which we're assuming exist because the space-time is globally hyperbolic. We are assuming, rather crucially, that the space-time has this flow property of global hyperbolicity. Well, let me come quickly to what I wanted to say about scaling. Partly, I realized that I didn't have all that much to say about scaling. I'm not completely satisfied with the treatment I'm capable of giving it at the moment. Perhaps one way of making this discussion is to say what's wrong with the theory of the definition of quantum field theory, which I've been trying to sell you. Is there anything wrong with it? Well, the answer is there are several things you can't prove, which you can't prove at present, which are absolutely crucial, and which you can prove if you put in the suitable scaling axiom. And I want to say a little bit about that, though I'm not really confident I have absolutely the best way of saying it. So what are the things we have problems with? Well, you see, one of the things that we're meant to be talking about positive energy when we talk about crystallization. That's meant to be how positivity of energy is encoded in the theory. But of course, on a general space-time, that's encoded in terms of an energy momentum tensor. Now that's meant to be a local operator then. It's meant to be something that belongs to these things OX, which we have introduced. But can we actually prove that it does? Well, no, you see, because you realize that even if you were terribly convinced by what I told you about what a field was, in ordinary quantum field theory, field operators are things which when you go to, certainly when you go to Lorentzian manifolds, need to be smeared. They're operator value distributions. And although this definition would give you a locally trivial vector space of these OXs on any space-time, we haven't introduced anything which would suggest that it was interesting to kind of smear things. So you see that there's another way we could have defined field operators in our theory. So in any theory of the general kind that I'm talking about, it's natural to say that a field is something, well, let's say just a scalar field to begin with. It's natural to say that when you have a space-time M, which is a cobordism from M0 to M1, in our usual situation, then it's natural to, you see, a scalar field would be something which you could integrate against a smooth density with compact support. And we'll say with compact support. So supposing we consider smooth densities with compact support, and let compact support mean away from the two ends of the coordinates. Then we could consider maps which, to each such thing, you could say a field operator was something which to each, a scalar field was something which to each such thing gave one a homomorphism from EM0 to EM1. And, well, what properties would one require of such a thing? Well, one could certainly concatenate this with cobordisms at each end, and then the densities on this would sit inside the densities concatenated on this, and would fit in with the operators that you had there. So there's a natural notion of functoriality with respect to concatenating things. We could say that a transformation of functors of this kind is a scalar field. And by tampering with the densities and making them tensor densities of various kinds, you could define tensor fields of any kind, like one-form fields or whatever, Riemannian metric fields. Well, the obvious thing that's defined that way is, of course, the energy momentum tensor, because the energy momentum tensor is, you see, to the space of cobordisms from Riemannian cobordisms from here to here, we get operators by our theory. Well, supposing we these are things which have a metric. Supposing we differentiate the operator with respect to the metric, then apart from the fact that they should be the dual of smooth metrics rather than functions, we would get exactly this structure. The energy momentum tensor is the derivative of the functor itself. You see, when the manifold can't change infinitesimally, the only thing that can change infinitesimally is the metric on it. And the derivative of the metric then is exactly something of this form. So it's reasonable to call this, I would call a structure of this kind a Whiteman field. So these are things which can be defined, and that's an alternative way of defining fields. And we have to say, are these things the same as smooth sections of the bundle that we have over there? And I don't see how we'd be able to relate the two things at all unless we make some more assumptions. So that's the first problem. First of all, defining an energy momentum tensor, and then more generally, seeing that these things have something to do with operator value distributions. So this is something about the way they behave when you move the point X as operators. Well, there are, I suppose the other problem is to, prove that there is a good relation between Lagrangians, the thing that physicists think is characterizing a theory, and theories of this kind. Now, the whole idea of this structure was to avoid having to introduce any kind of integration on infinite dimensional spaces, which is kind of a morass, and people haven't really succeeded very much doing it. So it's very important to at least be able to prove the natural statement which would come out of this. Supposing we have a moduli space, supposing we have a theory, at least we know exactly what a theory is in this definition. So we can certainly think of a moduli space of theories. So in this morning's lecture, we had a space like this of theories. And we have on it what's called the renormalization group flow. So we automatically have a flow on this, which comes simply from taking a manifold and rescaling its metric. I mean, you can multiply the metric by any real number you like and get a new manifold with a complex metric. So we certainly have a one parameter flow on our space of theories. It's not seems not very exciting, in that when you change the scale, the theory obviously isn't going to change very much. Incidentally, I was one thing actually, if I'd been brave enough, I would have asked the question this morning. I didn't really understand the notion of the global symmetries of a theory. I'd assumed that when one had a theory, it's an object of a category and it has automorphisms. And it seemed very implausible. I mean, if you think of the moduli space of tori, then there are certain tori that have bigger symmetry than others. And it seems strange that it should be constant over the moduli space. I wondered if what was meant, that was going to be my question, was one just meant to be saying that the automorphisms of the theory in question were constant along the trajectories of this group, I think, when you go from short distance to long distances, so to speak. Anyway, that's a possible question to ask at a later lecture to someone else. What we would like to be able to prove anyway in this picture is that when we consider our moduli space of theories and imagine making a deformation of it, we would like to be able to prove that that deformation does correspond to a field in either of the two senses which we would like to be the same. So we have now two different kinds of field. We want to know they're the same and that a deformation of a theory is one of them. If we could do that, then we would have a fairly good link between theories defined by Lagrangians and the theories that are defined by this axiom system, such as it is. Well, it seemed to me that what one needed to do was to have all of these problems could be solved, it seemed to me, although it isn't properly worked out, so I'm probably making exaggerated claims. If one adds just one assumption, which is a scaling axiom. In other words, we need to be able to say that we can smear cross sections of fields defined in the way that I said, and one also needs to be able to use that for one other purpose, which I'll have to postpone to the next lecture. The scaling property is just to do with the behavior. If we have a point X and we're considering all these disks around this, so supposing we have things of radius r for all r disks of radius r, we have all these spaces, let's just call them E sub r, associated with these things. They're forming an inverse system. Well, you can think of them as forming a bundle on the r-axis. This is the positive real numbers in there. So for anything except 0, we have an OR. Well, an ER let's call it ER, the thing associated to the disk of radius R. It seemed to me that the condition we need is that this can be extended from the line, the open line not containing 0, to the endpoint like this, so that vector space converges, or you can add on at the end something which you can associate to a sphere of radius 0 at the point. And then an actual field operator, you see, is a point in that definition. An element of OX is some kind of section of this bundle, and it will normally kind of tend to infinity in some sense as you come in, you see, because when we propagate outwards, we have a contraction operator, and the field is getting smaller as we go out. So these are sort of exponential functions coming down. Well, so if you could do that, then you could make a filtration of this space OX, as the way I've defined it, by saying that a thing has filtration K or something, if when you divide the thing, it's representative in radius R by R to the K, then it tended to a limit in this eventual space. So what would happen then was that you would then have a grading on the spaces OX, sorry, you'd have a filtration on the spaces OX by order of growth, and E naught would actually be the associated graded space to this filtration.
When you, may I ask, when you talk about this radius, it seems like you're in Riemannian signature.
Sorry? Yes, I'm talking, yes, sorry, I'm talking about, yes, I'm using the fact that it's all right to do this just on real things.
Okay, you
And
would
then,
rotate it.
and then we'll
Okay.
rotate it back.
Okay, I see.
Yeah, so we're doing this now in the real category. So if we added an axiom of this kind, I have the impression we can identify the two different kinds of fields. Because you see, this will enable one to actually give them some kind of density-like property on the manifold. And once we can smear them, then we can go between the two definitions, and we're kind of in business. The other thing, which I'm going to leave to the next lecture, I'm sorry, I've gone over time already, is that in order to begin to prove something about an infinitesimal deformation being given by a field, it seems to me we have to go from theories as I've defined them, the ones which are usually nowadays called extended theories. We have to go down at least one further layer. We have to add to our theory a structure which, to manifolds of codimension 2, manifolds of dimension d minus 2 in a d-dimensional theory, will associate some kind of linear category. I'll talk about that in the next lecture a little bit. It seems to me that we shouldn't need to go any further in depth with the theorem. But I'll say something about this property of making extended theories and how, at least in good cases, everything should be determined by the top layers. We shouldn't be adding more structure as we go down. The fashion nowadays is a bit to work from the bottom up, but I like to work from the top down in this situation. Anyway, I'm over time now, so I'll stop.
Questions?
The filtration was on O of X and naught is the associated gradient.
Yes, you see, supposing you took something, maybe you took a trajectory, which after you divided by r to the k tended to a limit. And you had something else, which when you multiplied it by a smaller power of r, tended to a limit. Then clearly, if you added the one to the other, you wouldn't change the limits that you got in here. So the thing that you got at the end would actually be the associated gradient. And you probably need to add some assumption like that the only degrees of growth that actually arise are probably just powers of r. I mean, maybe you need to put r to the k with log r and log r and that kind of thing, but I hope not. I mean, I think in the theories that are interesting in fundamental physics, you seem to get just integrals scale, or at least real number scaling degrees. But that's the kind of thing which I said I don't claim to have this properly worked out.
Would that property impinge on having, would you go to that limit, having a conformal field theory or something as a?
Yes, so a conformal field theory, this indeed, of course, works perfectly.
But in general, you might want to assume it's well behaved.
Yes, sorry, yes, I should, sorry, I should have said, this is obviously an attempt to formulate the property which is called asymptotically.
Freedom.
Well, we're saying that it's asymptotically conformal. Yeah. And of course, that's a crucial property. And which real physicists are interested in.
So in that list, there is typically one more condition that we typically care about.
Think a little bit louder.
On the list, there is one more condition we typically want to think about in physics, which I couldn't formulate in a way that I could
Oh.
present, which is analyticity.
Ah,
For example, the F matrix, whole structure have to be, is very controlled. It's analytic in a very particular way.
well, I mightn't be understanding your question properly, but I thought, do you mean the kind of thing which one says that the vacuum expectation values extend to things like what they call the permuted extended tube? Is that the sort of thing?
Not exactly. If I take the F matrix on the complex plane of momentum space, it has very controlled analytic properties there. And typically we demand QFTs when we write them down to be sort of well behaved, that you know, various observables that I would evaluate on the complex plane have to be well behaved. And it's always unclear how to make that point problem.
I certainly can't answer that question. I'd certainly like to hear more about it because I'd like to get clear at least what the question is in my own mind, which would take, I'd like to ask you more, to say more, but I certainly can't answer it.
Related to Constantine's statement earlier about the OPE. That one place where one way.
Then, I'm very happy for him to answer.
Other questions? Well, I have a question actually. So you mentioned the formations of theories coming from fields. Now, in topological field theories, we've been playing a lot with examples of extended operators, which are supported on submanifolds,
Yes.
which are not integral of point operators. So
Yes.
why do we expect in the quantum field theory every operator should be an integral of point operator, which is more or less, I think, what this is trying to get to.
Well, yes, actually, one of the many things I forgot to say was that here I was talking about observables concentrated at points, but it's clear that if you were to take any submanifold of your space-time, instead of looking at little disks around it, you could look at little tubular neighborhoods and do exactly the same thing, and you'd have a class of operators supported on that submanifold. Now, whether, nevertheless, as I understand it, physicists believe that you only need to deform, well, the theories are deformed by things of the kind I was talking about, and you don't, in deforming, you can put in an operator and make a different theory, so to speak, on some submanifold. But I'm not sure that you can actually deform a theory because it's, well, there aren't any canonical sort of submanifolds in a manifold. But yeah, I should have made some more comment about extended observables because that's clearly one of the things this formalism is sort of good for.
I had the same question during Ibu's lecture. He sort of wrote that every extended operator is an integral of some local operator.
That's an axiom. Sorry, I missed that.
Surprised by that.
I made the statement, if I have a Lagrangian, I can construct an operator.
Actually, sure. I mean, I mean, were you sort of saying that the automorphism group of the theory was constant along the renormalization flow?
So, and in
Or were you
RG flow,
really saying that it was the same everywhere on the moduli space? That seemed very
it
strange.
depends what you're calling the moduli space. If I have a Lagrangian theory with some parameters in the Lagrangian, I expect that I construct the operators, the observable related to that family of theories, and I the symmetry group that permutes those operators shouldn't depend on the choice of a parameter.
But see, I was thinking of things like, I mean, supposing you have the sigma model for a torus in two-dimensional theory with a torus target. So you have something like the in moduli space, which was space of. Well, surely when you have a torus which has some accidental symmetry, it's a very, then there'll suddenly be more automorphisms, even though that's just one particular point in the moduli space.
Typically, when you have accidental symmetries, it's related to some operators decoupling in some particular way. When you have accidental symmetries, it's typically related to some sector of the theory decoupling in some particular way. So if you don't allow things to decouple for operators, then the symmetry group should stay. That is a reasonable statement, and we observe it in many contexts.
I mean, supposing we take one like a sigma model with targeted torus. Surely tori which have just accidental symmetry, there's nothing sort of nothing deep about that, so to speak. You'll just get some more symmetries because the torus is symmetric.
Yeah, so when you have symmetries emerge accidentally, there's a statement of there is something happening to some set of operators. And, in many controlled way, when we see accidental symmetry, because an operator has decoupled from the field theory in some way. And store.
We can talk about
Yeah.
that.
One question.
We have a short break and we start again at